There it is. So we are glad to welcome you a second time to this webinar. So the floor is yours.
Thank you very much. It's a pleasure to continue this webinar and as part of this work group 4 in the cost action. And yes, as I already announced we saw it in the announcement of the webinar or the second part, I will get more into the direction of the positional games of graphs or on graphs, which is a topic that is probably the broadest of all in terms of how much was it researched and how many papers there are on this topic, etc., etc. So while in the previous webinar, I tried to touch upon these classic results, which are more related to the combinatorial games and theory combinatorial games, such tic-tac-toe, etc. Here we'll look at more things to do with games on graphs, and yeah, as I said, there are many directions in which you can go. That stems partly from broadness of the graph theory itself, and yeah, let me see and if I can take you in this direction step by step. Right, so the outline or the plan for the outline is we'll first repeat very shortly what positional games are. Actually, this talk as well, or this webinar will be self-enclosed, so you self-contained. We will not assume any previous knowledge from the previous webinar, although of course some experience is always welcome if someone attended it. But yeah, so I will introduce positional games and then give a couple of examples really in the direction of games on graphs, and then we'll say what games on graphs are, but step by step. First, we'll introduce a general criterion, actually probably the most important theorem in whole theory of positional games, and if there is one result that one should know is this general criterion called Euler-Selfridge criterion that I will introduce there. And then we will apply it immediately to the clique game. And then we'll talk again about the connectivity game, which is historically the first positional game on graphs studied. And then finally, we'll get to the threshold bias, which again, historically started the study of positional games under that name on graphs. This was the famous paper of Hvatal and Erdős, where the positional game name first popped up. Finally, yeah, I want to say a little bit about some research progress, like fast forwarding to this year. I was took part in an STSM within this cost action, current cost action on games, and then we have some results that I want to show you. These are also some positional games on graphs. Okay, so what is a positional game again? The positional game is a very simple structure where you have a collection. Essentially, it's a hypergraph if you're fond of these structures. So you just have, or other ways to say, just a collection of sets. So structurally, that's it. So you have a board. These are some elements. These are these little crosses that I'm drawing now. That's the board of the game. And then, so this is the board. And then the winning sets, what we call the winning sets, are a collection of some sets on this board. So these are some sets, subsets. So this whole thing is a subset of the collection of all sets, of course. And so we call this a hypergraph of the game, but we don't need the structure of the hypergraph much. That's the game. And then how do you play the game? Two players alternately claim elements of the board until all elements are claimed. Again, you can see them as we usually actually see them as red and blue. So red claims one element of the board, then blue claims one element of the board, and red claims one element of the board, and so on. And then until all the elements are claimed. So you can claim only unclaimed elements until all the elements are claimed. And then regarding determining the winner, we have several conventions. We have several standard sets of rules. Again, I talked about this a bit in the previous webinar, but I'll repeat them quickly. So strong maker-maker games, this is something like tic-tac-toe. If you have those winning sets, then red and blue would claim elements and so on. And then as soon as red has a whole winning set, red wins. As soon as blue has a whole winning set, blue wins. So whoever does it first is the winner. This is strong games. But then actually these are the most important of these four. The games that I will look at mostly today. These are maker-breaker games. In maker-breaker games, maker wants to claim a whole winning set like this. So if he manages, the red maker, if he manages to claim all elements of one winning set of this hypergraph, he's the winner. But then breaker wants him to prevent him from claiming a whole winning set. So breaker would like to put one blue element in each of the elements of the hypergraph. So if you look at the hypergraph, if breaker manages to put one blue mark in every winning set, that automatically is enough to conclude that there is no completely red set, and that means breaker won. So breaker as blue wins that way. So breaker just wants to prevent maker from winning. So these are maker-breaker games, and they're also the misère version of these. Essentially, is the avoiding games. I will not discuss them in detail here. Let me just say they're essentially the same structure, the same course of the game, but avoider would like to avoid doing this. So you lose if you do this. In the strong games, if you do it first, you lose. And then in the avoider enforcer games, avoider tries to avoid and enforcer would like to force. Anyway, let's get back so to get confused about too many notions. Let's get back to maker breaker games. These are the ones that we will look at. And if you let's look at an example of a game actually on graphs. So a game that I want to look at is a game, triangle game on edges of K6. So the board is edges of K6. So if you can look at this, this is a K6 complete graph of 6 vertices, but all the edges are white. Yeah, maybe that's a weird way to say it, but anyway, this is looks like an empty graph. Anyway, all the edges are white. So each player, when it's his turn, claims one edge of this graph. So, and what is the goal? Maker wants, so it's all triangles. Maker would like to have a red triangle, and breaker would like to kind of prevent maker from claiming a red triangle. This is the setup. Anyway, this is one course of the game. Could go like this. So maker claims this edge and breaker claims this edge. Then maker claims this edge and breaker has to claim this edge, otherwise he loses. And then if maker claims this edge, automatically he wins in the next move. Why? Because there are two of these threats, and obviously breaker cannot block both of them. So maker will say if breaker takes this one, maker will claim this one, and here's our triangle, and maker wins. So this is proof by example, sort of. Actually, we can formally prove it. We discussed that last time. This is a maker's win. This game. So by the way, this is an important thing. It's like each of these games is a combinatorial game with sequential moves and perfect information, and we know that one of the players has a strategy. So every maker-breaker game has two outcomes. It's either maker's win or it's breaker's win. And just by studying the game tree, we know that exactly one of those two players has a strategy. And actually, most of this, or much of the research, is about determining which of these two is the case for a given game. Okay, and that's it of the introduction. Actually, now actually, I would like to approach that what I advertised as the most important theorem. And the most interesting in my case, in my understanding, the theorem of positional game theory as a whole. And let's approach it by a warm-up example. And that's something that at first sight doesn't have much to do with games, but we'll connect it soon. Covering hypergraphs. What is that? Well, a hypergraph is K uniform. I will need that. If all the winnings, all those sets in the hypergraph, all the hyper edges, if you wish, have the cardinality K. They are K element subsets. So for example, if you have this hypergraph is, okay, I'll draw one more, is 4 uniform. Each of the sets has cardinality 4. That means 4 uniform. Okay, and then if you look at, so a hypergraph is called two-colorable if it can be two colors such that no monochromatic hyperedge exists. So what does that mean? That if you have our hypergraph and then we color all elements of the board red and blue in such a way that every of these winning sets has both red and blue elements inside. For example, if these are the elements, this is the two coloring, this graph can be two colored. This is a two coloring. There's no monochromatic hyperedge in this hypergraph. Okay, and then the question that we want to ask is, what is the smallest number of hyperedges in a non-two colorable K uniform hypergraph? And this is a really important question that it has been asked already some time ago, and then it has been studied a lot. This is one of the central questions about many or like this generally discrete math having applications in many things branching out or based on somehow on hypergraph structure. So what is the question once more? So a non-2K colorable K uniform hypergraph, for example, if you have two uniform, an example of a non-two colorable two uniform graph would be, hypergraph would be this. This graph is two uniform, has three sets, three elements of the board, or three elements, three vertices. And this graph, you cannot two color this without creating a monochromatic hyperedge. So no matter how you color with red and blue, say if you color this one red, then to avoid this being completely monochromatic, you should color this one blue. To avoid this being monochromatic, you should color blue, but then you have a blue hyperedge. So this is a non-two colorable two uniform hypergraph. And three edges you cannot, so smallest number of hyperedges in such a graph is 3. With two is not enough. That is easy to see. So this would be 3 for K equals 2. So this question for general K, this is, as I said, very important question. And there is a famous theorem of Erdős from 1963, sort of officially or unofficially the first application of the probabilistic method, where he showed that this if a family has of hyper, so now a family collection of K uniform hypergraph or a collection of K sets has less than this many elements, then it is two colorable. So you can two color it. In other words, this is the lower bound for this cardinality of a non-2K colorable UK uniform hypergraph. Why? So based on this theorem or from this theorem, we know that for a graph to be non-2K colorable, it has to have more than this, at least 2 to the K minus 1 sets in the family. Okay. So let's prove this. How do you prove this? Well, you take a random two coloring of our board. So we take for every X in X, with 50% probability, we color it red, and with 50%, we color it blue. Oh, sorry. Blue. Okay. So this is and we do that for every element independently. So this coloring is we are trying to study it and see what is the probability that it is going to be proper coloring. So is it going to have a more chromatic set or not? So how to study that? Well, that's a little bit of simple probabilistic analysis that ends here. So we define for every set. So for every set of this family, every set A, we define YA as a characteristic random variable. So what does that mean? That means it's either 1 or 0 1 if it's A is monochromatic, and it's 0 if A is not monochromatic. Okay. And then if you look at the number of monochromatic edges of F, this is obviously the sum of those. If you sum ones for all monochromatic sets and zeros for all non-monochromatic sets, we actually count the number of monochromatic sets. So expected number of monochromatic edges of this coloring of the hypergraph is equal to the expected number of the sum, or expected value of the sum of these characteristic random variables here. But this then, since the expectation is linear, we have this as a sum of the expectations of each of those, and then it is a well-known, is easy to derive fact that actually expectation of a characteristic random variable is just the probability for that variable to be 1. So what is the probability this is 1? What is the probability that this set will be monochromatic? It will be monochromatic if all 4 of these elements are colored red. Probability for that is 1/2, in this case 1/2 to the power of 4. And then also it could be that all 4 are colored blue. That's also, and this is another 1/2 to the power of 4. So these are obviously the only 2 cases where this becomes monochromatic. So altogether, this is 1/2 to the k times 2, which is 1/2 to the k minus 1, so which we have here. And this is how many of those do we have? Well, as many as the family cardinality is. And this, because the cardinality by assumption of the family is less than 2 to the k minus 1, this is altogether less than 1. So the expected number of monochromatic edges of F is less than 1. That means there exists a coloring. This is because what is expected number? Expected number is an average number over all of those possible colorings. There has to exist a coloring without a single monochromatic set. So that's a proper coloring. So this graph automatically is not, hypergraph is not it's not a non-2k colorable graph. Okay, so this is a nice result that we want to connect now to positional games. Well, how do we connect it? We have what we call a make or break criterion, and it's a theorem that I promised. Erdős-Selfridge theorem from 1975. We are now moving to make or breaker games. If we have a family of winning sets in a make or breaker game, and we know this is the condition, if we know that the sum of all 2 to the minus size of the winning set over all winning set, if that's all together is less than 1, then F is a breaker's win. And this is the theorem. There's one note that in this theorem, breaker is first to place technical. We have also variant makers first. I will discuss it later. But I think it's smoother to first look at this case when breaker is first to play. So this is a very nice theorem. It's fairly general. Actually, this is one of the most applied general criterions in positional games. We have essentially a very easy to verify condition that really takes into account only the sizes of the winning sets. And if we verify this and this holds, we have that automatically the game is a breaker's win. We know the outcome of the game. And not only that, actually, as we will see, we also have an efficient strategy for breaker to win. So pretty much we know all that we want about this game. And I want to show you the proof of this. So if you, it's kind of quite straightforward and a nice application of what we call some kind of weight principle or principle potentials. Let's look at it. Let's first analyze it a bit. If you're a breaker and you're playing this game, playing a positional game, so we are playing, and then already some elements are played. Maybe this one and this one are blue. And now we're playing, and then as breaker, which of these winning sets are dangerous and which are not dangerous. So obviously, this winning set here has a blue element in it. So this winning set is not dangerous at all. It's already neutralized by breaker's element. Also, this element, this hyper edge, this winning set as well has a breaker's element. It's also neutralized. But then if we look at these two sets, for example, this one, let's maybe I use another color. So let's say yellow, has two unclaimed elements and two red elements. And this one has, let's say, this many elements. So then it's kind of easy to see or like hand wavingly, this A compared to B is more dangerous because it's closer to being completed to the completely red winning set. And this is actually this concept, this idea will be taken to be a proper potential function that breaker we use for this proof. So a danger of a winning set. Now let's look at one winning set. A danger of a winning set, which is not yet touched by breaker, is 2 to the minus number of unclaimed elements of the. So we have some already claimed elements. There are some unclaimed elements. So this would be 4 in this case, number of unclaimed elements of A. So 2 to the minus 4 is danger. The larger this 4, the larger this part which is still unclaimed, less dangerous the winning set is, less close it is to being completed. Okay, and then during the game we can define this potential function, which is the danger. The danger would be the sum of those. So for each set we sum up the same thing, 2 to the minus size of that set, but only the unclaimed elements. So this means really these yellow elements, size of the A minus maker's edges, maker's vertices. So if we have A is here, and there are some maker moves, and then there are some unclaimed elements. This here would be 3 in this particular case. And we sum them up over all elements of the board, over all winning sets which are not yet neutralized, which are not, they have no breakers elements in them. Okay. By the way, I hope it's clear, but let me point out, if you have any questions, please do ask them. And yeah, I'll be happy to have a dialogue. And it's really, yeah, these step-by-step proofs. If you don't understand a step, please ask, because yeah, we don't want to go to the next one until everyone understands the previous one. Okay. Yeah. So what is happening before the game starts with this danger? So this is danger defined throughout the game. In the beginning, the danger of the winning set is exactly this 2 to the minus size of winning sets summed up over all winning sets. This is exactly what we had. I'll go back. This is what we have in the theorem. If you see it in the theorem, this is the condition. So the condition says danger is less than 1 in the beginning. So this is a convenient thing that of course it's not a coincidence. This is what we wanted, and so the danger will be less than 1 before the game starts. Okay, and now it remains to see what happens with the danger as we go through the game. And the general thing, we will prove that this danger cannot go up. It only stays equal or can go down. Let's do that. And this is going to wrap up the proof. So if you have, so far, if you have some moves of breaker, we already played the game. Let's say 4 moves. We have 4 moves of breaker, 4 moves of maker. Then you look at the 5th round. So after the 4th round, the game is reduced to the following thing. So if you look at the board, we have the board. And then some elements are already claimed by maker, some elements are already claimed by breaker. The new board actually will be just this. We can remove these from these elements here from the board. Why? Because any winning set that has a blue mark, we can remove the whole winning set. And after that, we can remove this element as well from the game. If we remove all the winning sets containing it, let's say this one and this one. And then all the elements, if you look at, on the other hand, all makers elements, if we have them, this winning set is the same as this winning set here. Because like this, these are already claimed in this winning set. At this point, it remains to, you need to claim 3 more elements of the board. So you can as well remove these 2 and just look at the winning set as this. So we essentially remove all these, and also we remove the elements. So we would just so we are removing the red ones from a set, and also only sets which have no intersection with the blue are considered. And all the other sets are excluded like this. And this is our board after a certain number of moves. And now, what is the strategy of breaker? In the following round, after I rounds, breaker will claim the element which reduces the danger the most dangerous element. And what is the danger? Like he claims Z element of the board that maximizes this danger on that set, on that vertex. So if we have, so Z is a vertex such that when this element is played, the winning set on that Z are the most dangerous in the sum. So the danger of the element of those winning sets when summed up is maximized. That's the strategy of breaker. Okay, and now it only remains to wrap up. So this is the last part of the proof. So if maker claims MI, then the danger of the game increases. So the total danger after the, so again, let's look at what are we looking at. So there was maker's move, and then or sorry, it was M1, and then B1, and then M2, and then B2. These are, let's say, the first 2 moves. And then we are looking at these 2 moves here. We are looking at M3 and B3 now. This is the round 3 or I+1. So how is the danger going to change from this point to this point? So what is the change of danger over this one round, one pair of moves, one maker's move and one breaker's move? Well, danger is going to be what it was earlier, minus the part which changed because breaker played this element that breaker played. So breaker claimed this element. What is the change of the danger? Danger previously of this set was 2 to the -4, and let's say here 2 to the -5. But when breaker plays this danger, because these sets are removed, this danger goes to 0. So this is the change of the danger when breaker plays his element. And then when maker plays the element, what happens there in these sets? Well, it used to be before the move, this was 2 to the -4. Now after the move, this changes to 2 to the -3 because there's one less element. And this was 2 to the -3, it changes to 2 to the -2 after this red element was claimed. And that means that actually what happens is that 2 to the -4 is doubled, right? From 2 to the -4 to 2 to the -3, that's doubling 2 to the -4. So you can see that actually what we add all those. So the danger after maker plays increases by all this, because doubling actually is adding the same value again. And that's it. And then there is one more term which really contains those that contain both, because we actually have to account for that. If there is an element of the board in this winning set that maker claimed, and after that, sorry, breaker claimed, and after that maker claimed, then we remove this winning set after breaker played, and then this doubling here does not occur. So we have to subtract again those that contain both, those that are like this. So we shouldn't have added them here. So we have to subtract. Okay, and that's it. So, and now the strategy of breaker, this is where it comes into play. This was claimed by breaker as the maximum of this function. Hence, this is of course greater or equal in absolute value than this what maker took, because breaker took the maximum, maker took something. So this is greater or equal than this. And this is a positive value or non-negative value. Let me actually, it's a non-negative value. So altogether, we have this being non-negative again. So this danger just cannot increase. New danger is less or equal than previous danger. So if we look at our course of the game, we look at before these two moves, the danger can only go down or stay the same. And initially it was less than 1. Oops, sorry. Just have to get back to there.
Can I ask a question, Miloš?
Sure. Yes.
I'm sorry, it's going to be a really basic question, but do you have an example of a real game? I mean, in which this theorem can apply, and that
yes,
you are sure that turn after turn the danger decreases?
Yeah, I will show you an example just after I finish the theorem, and this is actually where we applied.
Okay, great.
It was historically really applied. Yeah, but right. So.
Okay, thanks.
Right. Yeah. So it will be shown. So let me just finish the proof. So the danger initially is less than 1. So yeah, initial danger is, let's write it like this. We have danger of F1. It's less than 1, then it's always less or equal throughout the process. At danger of the end of the game is then automatically also less than 1. As it's less than 1, in the end, there will be no winning set of completely makers. Because what is the danger of a winning set that is completely makers? Well, the danger is 2 to the minus unclaimed number, all the number of unclaimed elements, which is here 0. So it's a 0. So this is 2 to the minus 0, which is 1. So this danger is 1 at the end of the game, and the danger is strictly less than 1. Hence, there is no win of maker. So breaker wins. That's it. So this theorem, so this is a repeated theorem. It's simple on one hand, it's really applicable, and yeah, it's just one needs to check this condition. So just before we apply it, I just want to give a couple of remarks. So this condition, if the family is K uniform, all the elements are of the hyper edges are K, cardinality K, then this condition is even simpler. Just the family has less than 2 to the K elements. And then this breaker strategy is constructive because the breaker wants to maximize the danger, and that's efficiently computed. And then I will tell you just, yeah, so just remark if breaker is second to play, we just need to replace this 1 with the 1/2. Because the only thing that changes is that we want to look at maker's first move beforehand, and then look at breaker's first and maker's first as before. Like then look at these rounds. So maker's move will double at most everything, and this is why we have a 1/2 here. But also, like, there is a theorem with breaker is second. Okay. So in this case, if it's K uniform, the condition is F is less than 2 to the K minus 1. And this is a nice, this looks a lot like this Erdős theorem that I presented to you earlier. And actually, this is a nice connection that this Erdős-Selfridge theorem is essentially a way of de-randomizing this Erdős randomized approach to proving the existence of that coloring, proper coloring of that hypergraph. So if breaker wins as in a game, positional game as second, then F is automatically 2 colorable. Why is that? Well, breaker a second, he can break into every set. What does that mean? That means that if you look at the game, breaker a second will be able to claim one element in every one of the winning sets. And then maker is first, because being first is even just an additional strength of the player. Breaker can play the same strategy and also put one element in each of the winning set. So essentially, if breaker is second can win, he can win as first as well. So both players can play as breaker. Both players can apply the strategy of just trying to claim element in each of the winning set. And this automatically gives a 2 coloring. So we automatically de-randomized by Erdős-Selfridge theorem. We de-randomized that randomized proof of Erdős. And yeah, this is what I just said. This is the corollary that we have. This was the Erdős theorem, and now it's a corollary of our theorem. And then, yeah, this is what I just said. And then let's look at an application of the Erdős-Selfridge theorem. Here's Lisa for this what you asked. So what is now the game? This is what we call the clique game. We note it like this. The board is the edge set. It's like the triangle game that we had earlier in our example. So you're coloring some players. We had the K6, remember? And then players were claiming edges of this K6. And the question is not just, can you claim a triangle on K6? The question is, what is, here is the question. What is the Qn? Largest Q such that the maker can win on in this game. So you fix the 6, and you look at what is the largest clique maker can claim. So August on K6, maker can claim a triangle, but he cannot claim a K4. So this is not possible. So this Q is 3. Is this clear? Yeah, if there are any questions, or should I explain this more, let me know. Otherwise, so this is like 4. So if we have K6, so if we have n equals 6, in this case, then as written here, then this Q of n would be 3. The largest clique maker can make this game. Okay, and what we want to prove is that this is between half log n base 2 and 2 log n. Why is that? Well, let's apply the Erdős-Selfridge theorem. Our Erdős-Selfridge theorem applied on this to this game. So what do we want? We want to prove this. What is the actual thing we want to prove? We have our complete graph, and we want to look at all possible cliques. So let's say this one, and so on, where the cardinality of the vertex set is 2 log 2n. Okay, so this is the K. So these are the winning sets. We want to show that breaker can prevent maker from claiming clique this large. Okay, so how can we show it? When we look at the game where all cliques of this size are winning sets, and we want to show by Erdős-Selfridge theorem that breaker has a strategy. Therefore, maker cannot claim a clique of this size. Again, let me know if I should explain this more. So this is what I just said. We have a collection of cliques. How many? So do we have? We have n choose q cliques of size q of vertex set of size q, and each of them is of this size. So a clique, say if q was 3, this would be triangles. If q would be 4, this would be K4. So let's say for Q4. How many elements does a clique have? Well, it has 6 elements. 1, 2, 3, 4, 5, 6. Q choose 2. So it's a Q choose 2 uniform hypergraph of the game with this many winning sets. So think of them, if you wish, it like if Q is 3, that would be triangles. If Q is 4, this would be K4s. Okay. And this is all on n vertices. So the n is the, so it's a Kn is the board. Okay. And now we apply Erdős-Selkirk theorem. So we plug this into the condition. This is the condition. Once more, what was the condition? I'll just go back quickly. We have, where is it? Yeah, it's essentially it's here. For example, f is less or equal to than 2 to the k minus 1 or 2 to the k roughly. So we can plug this in. This is cardinality of f, and this is 2 to the size of the. So this was k, size of the is k uniform in that formula. So this is simply true because yeah, it's kind of easy just playing with the binomial coefficients, standard calculation. So since this holds, we know that it's breaker's win, and breaker prevents maker from claiming cliques this size. So that's what I just said. Maker cannot claim a clique with this many vertices. And then on the other hand, we just have a standard argument by Ramsey. That's what I talked about last time, but it's also kind of easy. If n is larger than the Ramsey qth Ramsey number, then by strategy stealing, maker can win. I will not discuss this much. It's not like we primarily wanted to discuss or demonstrate the application of Erdős-Selkirk theorem. And then the real bounds actually are much closer, but also I don't need to talk about that in detail. So these are not the best possible bounds. The best possible bounds you can see below. Yes. And then generally, when we say positional games of graphs, we think of playing on edges of graphs. There's also some research done on vertices of graphs. But one important game is studied also before the definition of or the term coined about what's called positional games. We have what's called Shannon switching game. That would be the game in which essentially winning sets are all spanning trees. So maker would like, let me draw a picture. So we have our graph, base graph. Maker would like to have his graph connected. So if maker has this, like a spanning tree, and on top of that, possibly something else. Like in this case, maker 1. If maker has this, he wants to have a spanning connected graph in the end of the game. And breaker would like to prevent him. So what breaker wants, breaker on the other hand would like a cut, right? If breaker takes all edges in a cut and splits the graph into 2 so that maker has no edge across, then breaker 1. So that's called connectivity game. And there's this theorem, classical theorem of Lehmann, also quite interesting, and we can prove it now that we have these, what we developed already, what I told you so far. Maker-breaker connectivity game on the edges of a graph with maker playing second is a maker's win. It's maker's win if and only if G contains 2 edges joining spanning trees. And so first of all, proof is not hard to see. So if maker second can claim a spanning tree, if he can win, so like looking at this direction. If maker can claim a spanning tree, then also the second, so the first player, so if maker second can claim a spanning tree, then also the first player can claim a spanning tree. So both players can use the same strategy to claim a spanning tree simultaneously in the same game. So maker second has a strategy, this is the assumption. And then the first player with an extra move that cannot harm him in the first move can also claim a spanning tree. And that means really breaker will claim a spanning tree and maker will claim a spanning tree. Automatically there will be 2 edges joining spanning trees in the end of the game, one red and one blue. So this direction that straightforwardly follows. And then if you have 2 edges joining spanning trees, to see that maker can win as second. So if this is one spanning tree and this is the other spanning tree, so they are on the same vertex set, but I draw them separately to emphasize what I'm talking about. So if breaker claims one element, so breaker plays, let's say plays here, it splits this one spanning tree into two, then that edge in the other spanning, so this partition in the other spanning tree also partitions the spanning tree in two, and maker can reconnect the whole graph by playing that edge that plays across. And then this edge here, if we insert it in that other spanning tree, there will be more and more intersections of these two spanning trees, and then in the end, maker will claim a spanning tree that is intersection, complete intersection of these two. So that's also completing the other direction. And so if maker is first to play, the condition just changed to not edges join spanning trees, but spanning trees intersecting exactly one edge, because maker is first to play. And yeah, so if we let's apply this. So first of all, like this condition that we can apply this. It's a maker or maker's first to play is a winner if and only if G contains two edge disjoint spanning trees intersecting. Sorry, not edge disjoint spanning two spanning. Oh, let me maybe write it less condensed. Two spanning trees intersecting in one edge. So this is the condition if maker is first to play. Why? Because this one edge is what maker will play first, and then in the end, for the rest of the game continues as the same as in the proof I presented. And then having this in mind, we can look at one example, one thing that directly follows from this. So there is a game that you may know. It's a sort of popular game, relatively, or just like people play it as like for fun. So this is the beginning of the game. This is how the board looks like, and then each player, red is first to play. Red can connect two of these islands by a bridge, and then breaker, or like no, sorry, breaker second, blue can connect two of the islands as a bridge. And if this bridge is played, then of course red cannot play this anymore. So this is not allowed, right? So this is the idea. So like each of these middle spaces can be either occupied by a blue bridge or the red bridge. One excludes the other. And the goal of red is to connect the red sides, and the goal of blue is to connect the blue sides. And obviously, two cannot happen at the same time. One will happen and the other will not happen. There is this connection with hex to show that there is no draw. In this particular game, it's a red player's win. Red wins because there is this red path. Where is it? Somewhere here. Okay. And then one remark using this previous theorem of Lehmann, we can show that this is actually the first player's win. Red, as first player, has a strategy to win. Well, how to see that? Well, first, notice that like this structure here is the same as the board. So you look at what is the goal of red. The goal of red is to connect this here, which can be presented as a vertex, and then to connect it to this here, which can also be presented as a vertex. So if we join this one thing into a vertex, then this is the structure. So this is one side, this is the other side, and then note this is how the structure is. So you can play when you play here. That means you would connect so this would be the edge in this representation. Okay, so otherwise the structure is the same. I hope it's clear. So we just transfer this structure down. Okay, and now this graph that we have here, this graph is split into two edge joint spanning trees that actually not an edge joint, but they intersect in exactly one edge, that lower red edge that is shown in the lower part. So if you look at it, a green graph with the red edge is a spanning tree. And then the rest of the graph that is not green is also an edge, a spanning tree, which you add this red edge. So really directly we can apply Lehmann's theorem, and we can see that red player has a strategy. How? Well, red will play this red edge. If blue plays this, that means that blue disconnects the green part into this and everything else. And then all red needs to do is reconnect this green spanning tree by claiming one of the non-green edges between this part and the rest of the green. Now, if blue plays within the non-green, for example, let's say here, well, let me see where, for example, here, then this is where this part is disconnected. This part of the non-green is disconnected from the rest. Then red can play this and reconnect this part of the non-green with the rest. And this continuing these two disjoint trees intersect on more and more red edges until red spanning trees claimed. And there is more actually. Yeah, there's much more. As I said, there are many results that follow. I just want to maybe fast forward. See, yeah. So I want to show you this. This is like I already talked about connectivity game. There's also Hamiltonicity game, which the obvious winning sets were. So this connectivity game, as I said, are spanning trees. Maker wants a spanning tree. Hamiltonicity game, Maker wants Hamiltonian cycles. And H game is like a triangle game where H is a graph, fixed graph. So these are probably three of the most studied and most important games. And then there's been a number of papers about them and other games. Maybe I can just mention a bit that like well, probably the first problem studied was the so-called biased games, where Maker claims one element. So you play on the complete graph. Maker claims one element of the board and Breaker claims B elements of the board, and then you look at which bias of Breaker is enough for Breaker to start winning in a game. Because like if you look at the connectivity game on a large graph, it's very easy for Maker to make a connected graph if you play one against one. So if you play one Breaker, one Maker, it's easy to connect. Let's say we play on 100 vertices, and half of your red edges obviously will have a connected graph. But what if Breaker plays 2 elements per move and red plays 1? What if Breaker plays 3 and Maker plays 1? At some point, Breaker starts winning. This is also introduced by Hvatal and Erdős in the seminal paper. And then we look at the threshold bias. This would be where, so maybe I have a picture. I'll just show you a little bit about like to give you a flavor of this. As you increase this bias in a one against B game, at some point Breaker starts winning, and this is the threshold bias that we're looking at for these games. And I can just maybe show you as again, yeah, also like as a one slide where you just have results which are these classical results that really paved the way into studying positional games and graphs. These are the results about these 3 games where you have the threshold bias determined. Non-major question still is like, what is the leading constant here? And that's been open. Okay, and the remaining couple of minutes, I just maybe mention a bit of the last topic that I want to mention is like this our recent research. I wanted to this is quite specialized compared to the classical results, but I wanted to mention it because it's done within our cost action, and this is done as part of my STSM mission. I visited Faculty of Mathematics and Computer Sciences in Poznan in March this year, and I worked with Małgosia Bednarska-Bzenga and Sylvia Antoniuk and Tomasz Wurczak, who are actually all are experts. Actually, one of these results that I advertised as seminal is the result of the 2 of them. So I just will quickly go back to just show you here. You see Bednarska-Wurczak. These are the 2 authors for the threshold of the H game. And yeah, so we eventually studied so-called token maker breaker games. Let me just maybe give you a flavor of what it is. So what are token maker breaker games, or in general? first of all, not looking at graphs, but general. So token, if you have your hypergraph, then each player has a limited number of tokens. Let's say Maker has just 5 tokens. And as you play, you use your tokens. So this was just 1 token that I used. Next time I play, I used another token, and so on. Once I'm done with all the tokens and I played all my moves, next time I want to play, I have to remove 1 token, or I have to use 1 of those tokens to play it somewhere else. So it's harder for Maker if Maker is bound by the number of tokens he can use. It's harder for Maker to play home winning sets. And we studied these standard games on graphs, but really through the lens of this token approach, where we know Maker is winning, but we reduce the number of tokens, and then at some point Maker cannot win anymore. This is the thing, the value we wanted to study. And this token approach is a standard approach with obvious possible kind of things related to them, as with many ordinary games, combinatorial games, we have this limitation. Okay, and that's all I wanted to say. I'll just leave this slide on, as we have as I advertised last time, we have a book. Yeah, this is okay. It's now visible. There are 2 books on positional games. One is a great standard book, or a classical book by Beck, and the other is the one we wrote in 2014. Sorry. Yeah, if you want a PDF of that book, here's the link or a QR code. Yeah, and I'll stop here. Thank you.
Great, thank you very much. Thank you very much. It was really clear, for me at least. So I guess we don't have much time for question or remarks, but perhaps, and as you can see, we have few members in the session, but perhaps Emin or Sam, you have a question, especially because you were on there the first session, if I remember correctly. If you're still there. No, it was clear. Okay. Yeah, actually, I just have one question, / remark. When I ask if you had a real example to show us to highlight the results, I was more thinking about a game that would exist in real life, you know, I mean, like board games, or not necessarily a game that you will, because I have the feeling that the triangle game, it's something that you kind of invented to give an example of this result. Do you think, or is it possible to apply this result on like an existing game, something that you can buy in a game shop, for example? Do you have an example of that?
Yeah, well, regarding that, I do have some examples. Yeah, maybe I can stop. Yeah, okay, now I see you better. Yeah, so there are examples of some generalizations of tic-tac-toe where already this applies. So you have if you have these n to the d tic-tac-toes, and then several of those already for small values of n and d, you can directly apply Euler-Selfridge theorem to get this conclusion. Also, this infinite n in a row versions, where you play on the infinite board, you want n in a row, like sort of some derivatives of Go and similar games of that kind. There are also examples where you look at the board, split the board into parts, apply Euler-Selfridge theorem, and then you get automatically bounds for the conclusion that you cannot make certain number in a row. So these would be examples of real games. As what you asked, like, you're right. I mean, these games more originate from problems in graph theory, and then the games actually are helpful more for like having implications in graph theory. That's actually how Erdős initially, and Fatal, and then this Euler-Selfridge, etc. Those games defined for graphs were more helpful for having implications in graph theory, as the one I presented. Like, you have automatically an efficient algorithm to find this the randomization of that randomized coloring, for example. That's like applying the game in that direction. So, but that I mean, I know that it's an opposite direction of what you asked, but I just figured it's a connected thing.
Yeah, sure.
But yeah, so it's of course this thing to have in mind. Several games that are really played and you can buy. They turn out to be positional games, maker breaker games. If that's the case, then one can always try to apply errors of Selfridge, check the condition for errors of Selfridge, and automatically giving. I mean, the beautiful thing about this is like this is something very rare. Generally, in combinatorial games, is that you have a theorem that is general, and it really just by checking some numerical value, like really this such a simple condition, it just simply readily gives you the outcome for the whole family of games.
Yeah.
So yeah. Having in mind this power, it's like it would be really like every case of these is like a rare gem, I think, in that respect.
Okay. Well, thank you. And I have like just one last question, and it's gonna be more a broader question connected to how you, as a mathematician, you produce results and how you use game in your researches. So my question is, how often, or do you always connect to a game that you try to play with someone else? I mean, with a colleague of yours, or have you reached this point where you don't need to try on a board or on a graph, and that you already have the structure in your mind? I mean, how? You understand my question? It's a really meta thing, but this is how that's the question I have when I see you, mathematician, dealing with games and thinking of how do you use the object to produce a result, or to verify a result, or to have an instinct of a result.
Yeah, that's a very good question. I mean, I've been asked that a lot, or we discuss it a lot. It's like there are those playable games, and then there are those, obviously, when you let n tend to infinity, and you have n whatever 2 to the n moves where n tends to infinity, that's not going to be played very often. And then some of these games are interesting to play in a small example. Some of those games even have, as a building block, have a small case. And then we even looked at those. Some of those we managed to solve by some explicit arguments. Some of those can be studied by a computer. Some of those, of course, simultaneously, they are interesting to play on these small boards. But as you said, some of those results, we just really know how the behavior is. For example, like these things related to random graphs and random networks. There are many interesting questions about games on networks. And then there really the question is, and what happens when n is large? What is the limit case of this graph process that we have as a result of the game? And there you don't actually play it. You just imagine this process being played essentially in the background, but it wouldn't be really a human playable game, more like an algorithm, or two algorithms, one against the other if there are two players, just that produce the process.
Okay. Yeah, I think it's an interesting question because it raises then epistemological question about what is the nature of the game when you do research in mathematics, whatever kind of mathematics you used to for example, to give the strategy of a game, and then how it drives the entire research. So this is a kind of question that I'm trying to deal with, even though I don't really have an answer how to start the research with. But I think it's interesting to have this question as well from an epistemological point of view, like what is the nature of the object you're dealing with? That's one of my main questions. That's why I'm curious about that.
Yeah, that's very nice. I mean, I've been exposed already as I'm actively participating in this cost action. There are all those different views and different perspectives that you, and then I'm beginning to think about things that I haven't thought about before. But this is these kind of questions where you just wonder about the playability, for example, that would be, or like measuring playability. That's also I had the opportunities to hear about. Is like that's an interesting thing to kind of cross with games like this.
Yes, sure, definitely. Well, anyway, thanks again for the second part of this. It was really, really interesting. And so I guess we can stop now. So next date, it's in October, around the 21st, if I remember correctly. I don't have my agenda in front of me, but so just spread the word, and also that spread the word, it's recorded. So if you want to have a second watch or a first watch, but not on the right time, then please do it. That's so thank you very much, Miloš, and so let's hope to see you later in another webinar, and have a nice evening, you three.
Thank you very much, and thanks all for the attention, and
no problem.
It was really a pleasure.
It was really, really interesting. Okay,
happy
so bye bye.
again.
See you
Goodbye.
later.
Bye.
Bye.